In the annals of military history, there are moments when the tide of technological warfare shifts, not through grand inventions, but through seemingly simple innovations that confound even the most brilliant minds. Picture this: the German Reich, a nation that had revolutionized armored warfare, that had engineered the fearsome Tiger and Panther tanks, that had developed rocket technology and jet aircraft, found itself completely baffled by what appeared to be nothing more than a hollow shell filled with explosives. This wasn't science fiction, this was World War II, and the weapon in question was the Allied high-explosive anti-tank round, better known as HEAT. Imagine the most advanced military in the world, renowned for its engineering prowess, utterly stumped by a single piece of enemy technology. That's exactly what happened when German engineers tried to reverse engineer the Allied heat shell during World War II. Why, despite their ingenuity, did this seemingly simple projectile prove to be an insurmountable obstacle? The answer to this question reveals not just a tale of wartime technological struggle, but a profound lesson about the nature of innovation, the importance of fundamental research, and the hidden complexities that can lurk within what appears deceptively simple. To understand this remarkable story, we must first transport ourselves back to the early years of World War II. The German Blitzkrieg had swept across Europe with unprecedented speed, and at the heart of this success was the Panzer Division. German armor seemed unstoppable, and the Allies were desperate for weapons that could effectively counter these steel behemoths. Traditional anti-tank weapons of the era relied on what we call kinetic energy penetration. Essentially, you fired a very hard, very fast projectile at armor, hoping that its momentum would carry it through. The thicker the armor, the larger and faster the projectile needed to be. It was an arms race of mass and velocity, and it was reaching its practical limits. Then came the breakthrough. Allied engineers, building on theoretical work that had been largely overlooked, developed a revolutionary approach to defeating armor. Instead of relying on the kinetic energy of a fast-moving projectile, they harnessed the power of a precisely shaped explosive charge. The high-explosive anti-tank round was born, and it represented a paradigm shift in anti-armor warfare. Unlike conventional shells that needed to be fired at high velocity from powerful guns, heat rounds could theoretically penetrate thick armor regardless of the weapon's muzzle velocity. A small, lightweight launcher could potentially destroy the heaviest tank. This was nothing short of revolutionary. The first Allied heat rounds began appearing on European battlefields in the early 1940s. British and American forces deployed them in various forms, from bazooka rockets to artillery shells. German tank crews and intelligence officers quickly realized they were facing something entirely new. Tanks that should have been impervious to light anti-tank weapons were being penetrated and destroyed. After-action reports began flooding in, describing impossible penetrations, armor failures that defied conventional understanding. German military intelligence collected fragments, captured unexploded rounds, and began the process that had served them so well throughout the war: reverse engineering. The German war machine had a well-earned reputation for technological adaptation. They had captured and improved upon enemy designs before. Soviet tank designs had influenced German armor development. British radar technology had been studied and countered. But the heat round was different. When German engineers first examined captured Allied heat shells, they must have felt a mixture of curiosity and perhaps even dismissiveness. The design appeared almost crude in its simplicity. There was no complex mechanical fusing mechanism, no intricate guidance system. It was essentially a shell casing containing explosives with a cone-shaped cavity in the front. How could something so apparently simple be so devastatingly effective? The answer lay in a phenomenon that had been discovered decades earlier, but remained poorly understood: the Monroe effect, named after American scientist Charles Monroe, who had observed it in the late 19th century. When an explosive charge is detonated against a surface, the force radiates in all directions. But Monroe discovered something remarkable. If you created a hollow cavity in the explosive charge, particularly a cone-shaped one, the detonation would create a focused, high-velocity jet of explosive gases and material that could penetrate materials far beyond what the explosive alone could achieve. This wasn't a simple explosion. It was a precisely orchestrated hydrodynamic phenomenon that transformed solid matter into a lance of superplastic metal traveling at speeds that could reach 10,000 meters per second.
Let's pause here and truly appreciate what this means. We're not talking about melting through armor, as popular misconception often suggests. The temperatures involved are indeed extreme, often exceeding the melting point of steel. But the penetration happens far too quickly for melting to be the primary mechanism. Instead, what occurs is more akin to a hydrodynamic process. The shaped charge creates such extreme pressures that the metal liner and the target armor temporarily behave like fluids. The copper jet that forms doesn't burn through the armor so much as it flows through it, carving a channel through what was moments before solid steel. The physics involved operates at the boundary of solid mechanics and fluid dynamics, in a realm where conventional intuitions about material behavior simply don't apply. For this process to work effectively, everything must be precisely calibrated. The explosive charge must detonate uniformly, creating a symmetrical collapse of the shaped cavity. The cone itself must be manufactured from specific materials with exact properties. The standoff distance, the gap between the shaped charge and the target, must be optimal to allow the jet to fully form before impact. The slightest imperfection, the smallest asymmetry, and the jet becomes less focused, less effective, or fails to form properly at all. This was the magic that German engineers needed to unravel, and they found themselves facing obstacles at every turn. The first challenge was the liner itself. In effective HET rounds, this cone-shaped cavity was lined with a thin layer of copper, but not just any copper. The copper needed to be extraordinarily pure, with a specific crystalline structure and precisely controlled ductility. When the explosive detonated, this copper liner would collapse inward and be transformed into the penetrating jet. The quality of this jet, its velocity, its coherence, its penetrating power, all depended critically on the properties of the copper liner. Allied metallurgists had spent years perfecting the processes to create copper with exactly the right characteristics. They understood the relationship between grain structure, purity, and ductility. They had developed quality control processes to ensure consistency. German engineers examining fragments of captured shells could see that copper was used. They could measure its thickness and basic composition, but what they couldn't see was the hidden complexity in how that copper was produced. The specific smelting processes, the controlled cooling rates, the rolling and annealing procedures that gave the copper its optimal properties, all of this was invisible in the finished product. They could analyze a piece of copper and determine that it was very pure, but the path to creating that purity, the industrial processes required, represented decades of metallurgical knowledge and infrastructure development. Germany's industrial base in the early 1940s was already stretched thin. Copper was a strategic material in high demand for electrical applications, shell casings, and countless other military needs. The idea of diverting limited copper supplies to develop a new, uncertain technology when existing anti-tank weapons were still considered adequate faced significant institutional resistance. Moreover, the specialized facilities needed to produce high-purity copper with controlled properties were not readily available. Building such facilities would require time, resources, and expertise that Germany simply couldn't spare in the midst of a multi-front war. But the copper liner was only one piece of the puzzle. The explosive itself presented its own challenges. HET rounds required explosives with specific detonation velocities and pressure characteristics. The explosive needed to be stable enough for safe handling and storage, yet powerful enough to generate the extreme pressures required for jet formation. It needed to detonate uniformly, without irregularities that would disrupt the symmetrical collapse of the liner. Allied chemists had developed specialized explosive formulations, often proprietary blends of various compounds, each carefully chosen and proportioned to achieve the desired characteristics. German explosive experts were highly skilled. They had developed their own sophisticated explosives for various applications. But reverse engineering an explosive formulation from fragments is extraordinarily difficult. You can analyze the chemical composition, identify the compounds present, but determining the exact proportions, understanding any stabilizers or additives, recognizing subtle processing techniques that affect the explosive's crystalline structure and sensitivity, all of this requires extensive testing and experimentation. And experimentation with high explosives is time-consuming, dangerous, and resource-intensive.
Then there was the detonator, perhaps the most critical and most underestimated component. For a shaped charge to work effectively, the explosive must be initiated uniformly across its entire base. If one part of the explosive detonates even microseconds before another, the resulting asymmetry will distort the collapsing liner, degrading or destroying the jet. Allied engineers had developed specialized detonators that ensured precise, uniform initiation. These weren't simple percussion caps. They were carefully engineered devices that converted a mechanical impact or electrical signal into a perfectly symmetrical detonation wave. The precision required is difficult to overstate. We're talking about timing differences measured in millions of a second, dimensional tolerances measured in fractions of a millimeter. German engineers examining a damaged or expanded heat round might not even realize the critical importance of the detonator's precise functioning. The device would often be destroyed in the detonation, leaving little for analysis. Even if an intact detonator was captured, understanding its operating principles without extensive testing would be nearly impossible. And producing such detonators consistently at scale required manufacturing capabilities and quality control processes that were extremely demanding. Beyond these material and component challenges, there was a more fundamental issue: Germany's military doctrine and institutional thinking. The German military had invested heavily in kinetic energy anti-tank weapons. They had developed some of the finest tank guns in the world, firing armor-piercing rounds at high velocities. Their doctrine emphasized the importance of muzzle velocity and projectile mass. The entire German anti-tank philosophy was built around this approach, from training to tactics to industrial production. Heat rounds represented a completely different paradigm. They violated the established wisdom that more velocity and more mass meant more penetration. Military institutions are inherently conservative, and for good reason. In war, reliability and proven effectiveness matter more than theoretical innovation. German military leadership was understandably reluctant to divert resources from proven weapon systems to develop what seemed like an exotic technology that they didn't fully understand. There were generals and engineers who saw the potential of shaped charges, but they faced an uphill battle convincing their superiors to make the necessary investments. This institutional inertia was compounded by Germany's increasingly desperate strategic situation. By the time heat rounds became a significant concern, Germany was fighting a multi-front war, facing material shortages, dealing with bombing campaigns that disrupted industrial production, and struggling to maintain production of existing weapon systems. The idea of undertaking a major research and development program to master a new technology when resources were desperately needed just to maintain current production levels was almost inconceivable. Germany was forced to make hard choices about resource allocation, and heat development consistently lost out to more immediate priorities. The German response to the heat challenge revealed another critical factor: the importance of fundamental scientific research. The Monroe effect had been known for decades, but truly understanding it required sophisticated theoretical physics and advanced experimental capabilities. You needed high-speed photography to observe jet formation. You needed precise diagnostic equipment to measure temperatures, pressures, and velocities during detonation. You needed computational resources to model the complex hydrodynamics involved. The Allies, particularly the Americans, had invested in this kind of fundamental research infrastructure long before the war. Universities, government laboratories, and private research institutions had been studying shaped charges and related phenomena, not necessarily for military applications, but out of scientific curiosity. Germany had its own excellent scientific establishment, and German physicists and engineers had contributed enormously to fundamental science. But the specific expertise and infrastructure needed to understand shaped charge physics was unevenly distributed. The Allies had teams of researchers who had been working on these problems for years. They understood the subtle effects of linear geometry, the importance of explosive characteristics, the impact of manufacturing variations. This knowledge couldn't be replicated overnight, no matter how brilliant the individual engineers attempting to do so.
German attempts to develop their own heat rounds did eventually bear some fruit. They produced shaped charge weapons, including the Panzerschreck and various grenades, but these weapons consistently underperformed compared to Allied equivalents. German heat rounds often showed erratic penetration, poor reliability, and significant manufacturing defects. Batch-to-batch consistency was a persistent problem. A round that performed well in testing might be followed by rounds that failed completely, with no apparent explanation. This inconsistency was devastating for a military weapon. Soldiers needed to trust their weapons, and German infantry anti-tank teams often preferred other options when available. The quality control issues stemmed from the fundamental problem that German engineers never fully understood all the variables that mattered. They could produce copper liners that looked right, but without understanding the precise metallurgical properties required, they were essentially guessing. They could formulate explosives that seemed similar to Allied versions, but without knowing the exact specifications they were approximating. They could manufacture detonators, but without sophisticated diagnostic equipment, they couldn't verify that these detonators were achieving truly uniform initiation. The result was weapons that sometimes worked brilliantly and sometimes failed completely, with no reliable way to predict or control the outcome. This wasn't a failure of German intelligence or engineering capability. The individuals involved were highly skilled and dedicated. Rather, it was a lesson in the cumulative nature of technological development. The Allied heat round represented not just a single invention, but the culmination of decades of metallurgical research, explosive chemistry, precision manufacturing, and theoretical physics. It rested on an invisible foundation of prior knowledge, industrial capabilities, and research infrastructure. Trying to replicate it through reverse engineering alone was like trying to reproduce a gourmet meal by tasting it and guessing at the recipe, without understanding the cooking techniques, ingredient qualities, and preparation methods that made it special. The story becomes even more interesting when we consider what happened after the war. When Germany surrendered, Allied technical intelligence teams fanned out across the country, documenting German research and development efforts. They found extensive files on shaped charge research, detailed analyses of captured heat rounds, reams of test data from German attempts to develop their own versions. What's striking in these documents is how close German engineers came to understanding the principles involved, yet how consistently they missed critical details. They understood the basic physics of jet formation. They recognized the importance of copper purity. They knew that detonator uniformity mattered, but they never quite put all the pieces together in the right way. Conversely, when Allied engineers gained access to German research facilities and scientists after the war, they were impressed by the sophistication of German work in other areas of explosive technology. Germany had developed excellent armor-piercing rounds, advanced fuses, and sophisticated explosives for other applications. The gap wasn't in overall capability or intelligence, but in the specific expertise and infrastructure needed for shaped charge technology. It was a reminder that technological superiority is often domain-specific and path-dependent. The post-war period saw an explosion of shaped charge development as the underlying principles became more widely understood and shared. What had been a closely guarded Allied advantage became common knowledge.
The technical reports published after the war revealed the secrets that had so confounded German engineers. The specific copper alloys and processing techniques, the explosive formulations and their rationale, the detonator designs and their operating principles. Armed with this knowledge, nations around the world rapidly developed their own heat weapons, building on the foundation that Allied research had established. The implications of this technological race extended far beyond World War II. The heat round fundamentally changed anti-tank warfare, and by extension, the role of armor on the battlefield. If a lightweight, man-portable weapon could destroy even the heaviest tank, what did that mean for armored warfare? The answer drove decades of subsequent military development. Tank designers added reactive armor, composite armor, and active protection systems, all designed to defeat or mitigate shaped charge attacks. Anti-tank weapon designers responded with tandem warheads, multiple jets, and explosively formed penetrators. The action-reaction cycle of armor and anti-armor technology that had characterized World War II continued, but now shaped charge physics sat at the center of the discussion.
The legacy of the heat round extends into modern warfare in ways both obvious and subtle. Every anti-tank guided missile today uses some variant of shaped charge technology. The ubiquitous RPG series of weapons, which have played roles in conflicts from Vietnam to Iraq to Afghanistan, are direct descendants of those early heat rounds that so puzzled German engineers. Specialized demolitions, from breaching charges to oil well perforators, employ shaped charge principles. Even in space exploration, shaped charges have been used, such as in the deep impact experiments that studied comet composition. The physics that seemed so mysterious in the 1940s is now taught in engineering schools and applied in countless ways. But perhaps the most profound lesson from the story is about the nature of technological advantage in warfare. It's tempting to think of military technology as a straightforward competition, where the most innovative side simply wins. The reality is far more complex. Technological advantage depends not just on brilliant inventions, but on the entire ecosystem of knowledge, infrastructure, and expertise that supports those inventions. The Allied heat round wasn't superior because Allied engineers were smarter than their German counterparts. It was superior because it rested on a broader base of prior research, because it benefited from industrial processes developed over years, because it emerged from a scientific culture that valued certain kinds of fundamental inquiry. This has implications for how we think about technological competition today. In our current era, nations compete in artificial intelligence, quantum computing, biotechnology, and countless other fields. The temptation is to focus on the visible outputs: who builds the best system, who achieves the breakthrough first. But the heat round story reminds us that sustainable technological advantage comes from the less visible foundations: the quality of scientific education, the investment in fundamental research, the development of advanced manufacturing capabilities, the creation of institutions that can accumulate and transmit specialized knowledge. Germany's failure to replicate the heat round wasn't a failure of effort or intelligence. It was a consequence of the cumulative, path-dependent nature of technological development. You can't simply copy an advanced technology without also having the context of knowledge and capability that created it. This is as true as today as it was in the 1940s. When nations attempt to quickly acquire technological capabilities through espionage or forced technology transfer, they often find that having the blueprints isn't enough. The tacit knowledge, the industrial know-how, the ecosystem of suppliers and specialists, all of this matters as much as the explicit technical specifications. There's also a cautionary tale here about the dangers of doctrinal rigidity. German military doctrine's focus on kinetic energy weapons wasn't wrong per se. Those weapons worked well and had proven themselves in combat. But the institutional unwillingness to seriously invest in an alternative approach, even when that approach showed clear promise, created a vulnerability. Military organizations must balance the need for operational reliability with the willingness to explore and adopt new technologies. Too much conservatism, and you find yourself outpaced by more innovative adversaries. Too much pursuit of novelty, and you waste resources on unproven systems. Finding that balance is one of the perpetual challenges of military planning.
The human dimension of this story is also worth considering. Imagine being a German engineer in 1943, tasked with unlocking the secrets of captured Allied heat rounds. You're brilliant, well-trained, motivated by both patriotism and professional pride. You carefully examine the physical evidence, you design experiments, you test theories, and yet despite your best efforts, the technology remains elusive. The shells you produce work sometimes, but not reliably. The penetration is inconsistent. You know you're missing something, but you can't quite figure out what. The frustration must have been immense. You're aware that on the battlefield, soldiers are facing weapons you can't fully replicate, and that this technological gap might contribute to your nation's defeat. Yet the resources you need, the time you require, the expertise you lack, all seem just beyond reach.
On the Allied side, the engineers and scientists who developed heat technology probably had only a partial understanding of the broader strategic impact of their work. They were solving specific technical problems: how to make a more effective anti-tank weapon, how to improve jet formation, how to increase reliability. They likely didn't conceive of their work as creating an insurmountable obstacle for enemy engineers. They were simply doing their jobs, applying their expertise, building on the work of their predecessors. This is often how technological advantage emerges, not through grand strategic planning, but through the accumulation of countless small advances, each building on what came before. The heat round story also illuminates the complex relationship between theoretical knowledge and practical application. The Monroe effect was known in theory long before it was weaponized effectively. German scientists were aware of the phenomenon, but knowing that something is possible in principle is vastly different from being able to implement it reliably at scale. This gap between theory and practice is where much of engineering expertise lies. It's the realm of tacit knowledge, of tricks and techniques learned through experience, of understanding which variables matter and which can be ignored. This kind of knowledge is difficult to transfer even when nations are at war. When nations are at war, when you're trying to reverse engineer without access to the originating expertise, it becomes nearly impossible. As we reflect on this historical episode from our vantage point in the 21st century, it's striking how relevant these lessons remain. The specific technology may be obsolete, but the underlying dynamics continue to shape technological competition. Whether we're talking about advanced semiconductors, hypersonic weapons, or artificial intelligence systems, the same principles apply. Sustainable technological advantage requires deep foundations. Simple copying is rarely sufficient. Institutional culture and doctrine matter as much as individual brilliance. The accumulation of specialized knowledge and capability takes time and cannot be easily rushed. The Germans' struggle with heat rounds also reminds us of the importance of maintaining multiple approaches to problems. In hindsight, Germany's focus on kinetic energy weapons seems like a strategic error, but at the time, it was a reasonable choice based on proven effectiveness. The lesson isn't that Germany should have known better, but rather that maintaining parallel research efforts, even in technologies that seem peripheral or speculative, creates valuable insurance against technological surprise. The nation that can explore multiple technological pathways simultaneously, even at some cost and efficiency, may find itself better positioned when the landscape shifts unexpectedly. There's also an element of chance and timing in this story that shouldn't be overlooked. Had Germany encountered heat rounds earlier in the war, when its industrial capacity was less constrained and its strategic situation more favorable, the outcome might have been different. Had the war lasted longer, German engineers might have eventually cracked the code. Technology development has a significant stochastic element. Breakthroughs can come suddenly, or they can remain elusive despite sustained effort. This unpredictability is part of what makes technological competition so challenging, and why maintaining robust research efforts across multiple domains is so important. The post-war dissemination of heat technology also offers insights into how knowledge spreads once barriers are removed. After the war, what had been mysterious became commonplace with remarkable speed. This suggests that much of the difficulty Germany faced wasn't inherent in the technology itself, but in the barriers to knowledge transfer during wartime. In peacetime, through open scientific communication, international collaboration, and commercial exchange, technologies can spread rapidly. In wartime, each side must independently recreate knowledge, a far more difficult proposition. This has implications for how we think about international scientific cooperation and the balance between openness and security. As our story draws to a close, we're left with a technology that, while no longer mysterious, continues to shape warfare. Every modern military possesses shaped charge weapons. Tank designers must account for them. Urban warfare tactics are influenced by them. The physics that baffled German engineers is now part of standard military education. Yet the underlying lesson, that technological advantage is built on foundations of knowledge, infrastructure, and expertise that can take years or decades to develop, remains as relevant as ever.
The tale of the German struggle with Allied heat rounds is ultimately a story about the complexity of technological innovation and the challenges of technological catch-up. It's a reminder that what appears simple on the surface often hides layers of complexity beneath. It's a lesson in the importance of fundamental research, industrial capability, and the patient accumulation of expertise. It's a cautionary tale about doctrinal rigidity and the costs of institutional conservatism. And it's a testament to the dedication of engineers and scientists on both sides, who pushed the boundaries of what was possible under extraordinarily difficult circumstances. In the end, the heat round represents more than just a weapon. It's a symbol of how technological advantage emerges from complex interactions of knowledge, capability, and circumstance. It's a reminder that in the race of innovation, the visible breakthroughs rest on invisible foundations. And it's a lesson that continues to echo through our modern era of rapid technological change, reminding us that true mastery of technology requires more than simply copying what works. It requires understanding why it works. And that understanding is built on foundations that cannot be rushed or easily replicated.